Yeah. Guys, at this moment, I have access to no information about any of you because of the technical issues we have. How do I get to do this? All right.
So I just posted my email. Thank you.
Okay. Thank you. How do I get rid of this? All right, folks. Let's get back to where we were. We end up with vectors, and suppose you have a query. Now imagine that you have, so there is a two-phase narrative, right? You take all the documents that you have and you go index it. And then you feel proud as punch. You just got a vector database of your own, right? And in this vector database, now comes, you put a little interface application and say, okay, people can search. So when they search, when they enter the query term, what you will get is a query, a text. It may be a question, it may not be a question. Yeah. It may be anything. That text can be converted into a vector using our magic function, right? And what is that magic function? This sentence bird transformer. Yeah. The transformer architecture will do that for us. Then what happens is it will land somewhere. That orange dot that you see, that's where it has landed. In the vicinity will be some other documents, other vectors. All you need to do is find out which text produced those vectors. They are your search results, isn't it? So just keep track of the ID. Typically, you would have some ID associated with the text, and you can return the ID. Typically, for example, you'll use a library called FAS. FAS is one of the fastest libraries for approximate nearest neighbor search in vector spaces. So absolutely industrial strength, and it gives you the way to return you the IDs of the neighbors. And that becomes your search result. Now the question is, how do you find the neighbors? You need a notion of some distance or similarity, isn't it? Now, this is something unintuitive. I just told you guys in the mod that think in 1, 2, and 3 dimensions, and then extrapolate to higher dimensions. But actually, higher dimensions is a mysterious place because there is so much space there, just so much space there. You throw a million points at it, it's still empty, mostly empty. You throw a billion points, it's still mostly empty. So what happens is that if you randomly, if these points are getting sort of distributed within that sphere, within that space, then almost every point is very, very far away from every other point. Right? So see, it's a little bit like in Bay Area, here, the way we live. If you want to talk to your neighbor, you just have to open your window and have a chat. Don't even have to go to the neighbor's house. In Wyoming, if you want to talk to your neighbor, you get into the car and drive for an hour. Right? So high dimensional spaces, they are like Wyoming. Everything is far from everything else. Let me give you an intuition. Imagine that you have a line, right? A simple line, and you have 10 points to put. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. More or less, I distributed them on the line, right? But the same 10 points, if I put on a square, now you realize that maybe I put 9, but you can stick in a 10 somewhere. Do they look further apart? Right? Now imagine that I did it in a cube. And would you agree that now from the plane, they will evaporate and spread out, diffuse out from there. They'll be even further apart from each other. They're drifting apart, right? And you can imagine what would happen if your vector space is 1,000 dimensions. Right? So when it is so far away, if I just told you, you're looking for nearest neighbors, but if the meaning of neighbor itself is lost, you're in trouble, isn't it? Yeah. So do you have a situation in real life that you have encountered or where this happens? Anyone? See, guys, when you lie down on the ground and look up at the stars, right? Especially those of you who are in stargazing, you look at the immensity of space, the sky there. Then, and you know that it stretches out vast distances, unimaginable distances. When you tell your friend, look at that star next, close to that star, are they really close? No. For all you know, they may be very, very far apart, right? But your closeness is angle, the degree that those two are, the angle between them, isn't it? That's what you're looking at. So it turns out that in high dimensional space also, ultimately, you can use the notion of angle for neighborhood. Yeah? 2 points are close to each other. If the angle they make from the origin, right, like 2 points here, 2 points are next to each other, if whatever the dimensionality of space is, draw a line from the origin to that, make the vector, that's the vector. If the angle between the two vectors, A and B, is small, right, like say XB. If the angle is small, they do that. Are we together? And so you can use that in high dimension spaces. So it comes as a surprise to people that why are we not using Euclidean distance? Sometimes people do, but generally they don't, because the default distance that makes sense are dot similarity and cosine similarity, right? Alignment. How aligned are those 2 points? Does that make sense? Right. Now, what is cosine? So I've written it in mathematical notation. If you remember your vector algebra, it's just the dot product between two vectors. And cosine similarity is dot products divided by the magnitude of those. But now there's a small technicality for those of you who care that with cosine, you favor smaller text to emerge faster, emerge in the search results, and dot product favors the longer text.
Yeah, sir, can you hear me?
Yeah, I can hear you. Go ahead.
Sir?
Go ahead. Jax, you were saying something. Is someone trying to say something? Okay, I'll continue then. So there is also the thing about symmetric versus asymmetric search. These are the things that I'm just parking it in your mind. At this moment, you can just put it aside. What it means is when you search, if you know that you're using one document to search for another document, they'll be approximately same length. The query and the results will be about the same length. That is called a symmetric search. Are we together? The kind of search that we imagine is we just write some little 1 or 2 sentences and then nice big results come by. That is asymmetric search. So most of the time we do asymmetric search. Yeah. It is just and so there are certain models that have been trained to create that magic function better for symmetric search, and some models that have been trained to do the asymmetric search. That's all it is. Huh? So what we will do is, there is a little bit of Python code. And by the way, the coding part in machine learning in AI is quite simple. It's not heavyweight. For example, you do anything in UI or you do anything at the back end, you haven't begun to do something unless you have written 1,000 lines, isn't it? In no time, you're looking at 1,000 lines to do anything. In machine learning, most things are achieved in 3, 4 lines, 5 lines. Yeah? Because it's more about figuring things out than coding. So the coding is simple. If you don't know coding, but want to take a stab at it, please do try it, because it's easy to pick up, very easy to pick up. So as you can see, in one line, I invoked the sentence transformer and loaded a particular model into it. And then when you do that, it will download the model from the internet. Right? So there's internet repositories of it. Now I also loaded the corpus of text. You remember that? All of these texts that I put together, toy documents. So remember, this corpus is a toy corpus, right? Just a few little sample documents I put together. Right? And one of the things that you have to do is do it for something much bigger. Yeah. Your problem is, and that's why it's an easy lab today, you take this code, use essentially this code, but I want you to scale it out. Go get, I don't know, 5 documents in 5 subjects. Does that seem reasonable? And based on which machine you are, you can get, just make sure that the documents you feed in are text. Now, one task that you'll have to do is chunk it. Break it up into sizes no more than 512 words, tokens. The reason for that is this transform, the one that we are using, the simple transformer, it will, you know what happens when you talk to some friend and you go on talking and the friend says, wait, I'm beginning to lose you. That's pretty much how these transformers are. Their capacity to listen to you is only so much. 512 tokens. You give it 512 tokens, at worst 512 tokens includes full stops and whatever it is. That's why we don't use the word word. I mean, we mean words, but we want to include punctuations and other things, hyphens, numbers. That's why the general word token is used. So break it up into tokens and then create your search index and search into it and have fun. Okay. Most of the code is here. The only code I haven't given you is breaking it up into parts. Given a string, I trust is one line Python. At this moment, don't do an intelligent chunking, just do brute force chunking. What does brute force chunking mean? Literally fixed length. Set a length of 500 and just brutally chop the text into parts, split it into parts of 500 words each. Does that make sense? Or 400, or pick your number. Does that? So we'll do that. So anyway, we'll go here and I'm doing this. What am I doing? I am going to that and I'm giving it all these sentences that I have here. You see all these sentences? And I'm saying, okay, go create a vector database out of this. Create vectors out of it. Now, in this field, it's common to use the word vectors and embeddings interchangeably. I don't use the word embeddings to signify that these are not just any vector. These are vectors in the embedding space or the latent space. Right? Sometimes you'll also find researchers use the word latents. Right? Let me look into the latents, and it looks very cryptic. What exactly does it mean? It means the same thing. Right? So we take the embeddings, we look at its shape. It says that there are 16 rows and 768 columns. Right? What does that tell you now?
How the code is working first,
No, I can.
I did that percentage run NLP session.
Yes.
So what is that doing? That is loading.
Loading the corpus, loading this.
What is it loading it into?
Into this, at the end of it, hang on, you'll see that I created this thing, sentence made up of all of these sentences. It's just creating an array of sentences. That's all. You see that, array of strings.
Yes.
Very simple Python array of strings. Right. And that's all. Yeah, do please stop me to get that. And so you realize that so far I've not done anything. I've just invoked this. I've invoked this. This is like Aladdin and the magic lamp. This paragraph is simply rubbing the magic lamp and invoking the jinn, right? To be at your service. And it is at your service. And here you go. You give it your sentences. And what comes out? Text goes in. Array of text goes in. What comes out? Array of vectors. Right? So rows of vectors. In fact, 16 rows. So from that, you can deduce that how many sentences did I have in my corpus? 16, right? It is 16. You can verify 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So we got our 16 back. Now, what about the other thing? By the way, this is torch.size is a programmatic way of looking at the shape of a matrix. Now, what it means is that it has 768 columns, which means that each row, which is the vector for one text, what is the dimensionality of it? 768. There are 768 numbers representing one. Even if you give one word, it will explode into 768. If you give 1,000 words, it will still explode into 768. But one piece of text will become a vector of 768 dimensions, right? And you can see that
there are 16 words, right? And so that part we are clear. But what about the
768? See, think of it this way. You're projecting data into, so here, look at this. At this moment, data is in what dimensional space? 2?
2 dimensions?
So I can give it a value. Let's say that this one is x1, xi. I can give it a value, let's say 2.1, 3.6, something like this, isn't it? Does that make sense?
Yeah.
Right. And suppose I give you another vector, x2, another piece of text that came here, x1, x2 came here, and that would be represented with, let's say, 3.1, 1.8, something like this. So, one second, let me finish the argument. So you realize that I have 2 vectors, right? How would you write these vectors? You could write, or maybe there's a third vector, x3. So what you can do is x1, x2, x3. I can write it as 2.1, 3.6. This I can write 3.1, 1.8, and I can write something like, let me just put it minus 4.3 minus 3.6. I'm just putting it this way. I get a matrix, isn't it? In this matrix, how many rows do I have? 3 rows. 3 rows. And why do I have 3 rows? Because I'm representing 3 points, 3 pieces of text. And what is the dimensionality of the space in which I'm projecting this? 2-dimensional space. 2-dimensional space. So what should I say? What should be the shape? If I give all the 3 texts in an array, the matrix that I will get back, what should be the shape of it? 3 by 2. Right? Now you're getting it, right? So 3 by 2. It will be 3 by 2. Yeah. And now here we are talking about, so this is exactly that, except that the numbers are a little bit bigger. We gave it 16 sentences, so 16 is obvious. But look, the dimensionality of the space in which it is projecting is 768. Impressively big, right? Good.
How does that 768 number comes from? Do we provide any input?
No, when you create that transformer, when you train it, it is your decision to project it in that space. So people tend to take powers of 2 for sure, but even there, like 512 and 1024, you find the midpoint. You say that 512 is too small, 1024 is too big. Okay, let's take half. It's somebody's decision. But also it is, and let me introduce the concept of a hyperparameter search. See, what happens is that the bigger the space you take, right, the more numbers you have to store, your storage cost goes up, isn't it? Your compute cost also goes up a little bit, right? But the smaller you take, the more risk you have that it won't capture the semantics or the essence of the text. So somewhere in there is the optimal number. And people, through experience, through empirical studies, they figure it out. It's called hyperparameter search. They figure out what's the best size that works in the general case.
So the 16 is a 16
sentences
that you gave,
yeah.
sentences that you gave. That is separate from chunks.
No, think of it as a chunk, each chunk.
So let's say if we have 100 chunks, then will it be in this case 100?
100 times 768, exactly.
So each chunk is
a vector. Each chunk becomes a 768 dimensional vector. Is it making sense now, guys?
So Asif, sorry, only question is, right, that 768 number was not a parameter that we defined anywhere in the code that you have provided, right? So is that
Yes.
something that is automatically available in TensorFlow that it assumes
Yes.
768?
Yes. Not in TensorFlow, but yes. The guy who made this model, this particular model called MS Macro Distilbert Base 64, he thought that he's using a small model. Whenever you see the word distill somewhere, it means that it is the distillation of some bigger model. And one way to think of distillation, I mean, these things we cover on Tuesday's course in detail, but I'll give you an intuition. If the original model is the teacher, the distilled model is the student. So suppose you go and take a course in physics. Do you know as much physics as that professor of physics? You don't, but you have some ability, isn't it? Enough to get by. So distilled models are smaller models, baby models, because on people's laptops, etc., they run well. Okay? So whenever you see the word distill, remember it's a small. When you're dealing with a small model, it's not very effective to use a very high dimension space. And so judiciously, they have decided that the dimensionality of the vector space in which they'll embed is 768.
So Asif, one quick question. If you go to that the text that you have, so we have 7 sentence, but you have couple of paragraph. How are we fitting that paragraph into that in the program?
Very good question, Sanjay. Remember what I said. A sentence in English is the definition of a sentence is controlled in most languages by grammatical rules. In the NLP AI community, they have never heard of grammar. A sentence is whatever you mean it to be. It could be a couple of phrases, one word, or it could be an entire encyclopedia. Right? So the definition of sentence is very fluid in this field. One way to think about it is that a sentence is a logical unit of text or some meaningful unit of text for whatever thing that you're doing. Does that help with the intuition, Sanjeev?
So yeah, so I love physics, right? So it would be one sentence, right? Or I physics would be also one, right?
Yeah, absolutely. And in this particular case, for example, this poem of Devi is full of care. The whole poem is a sentence.
Okay.
Right? Each of these is from the point of machine learning. Each of these are poems. Some of you would remember. You may have encountered it during your education. Yeah. All of these are relatively famous sentences from different authors. So, are we clear now, guys? Any more questions? Make sure you ask because this is important to get.
So in the project, you're saying we should take much larger sentences, much larger blocks of
yeah.
So we'll have to chunk it.
Yeah.
So each chunk will become one unit that goes into
one unit, one sentence. Each chunk you'll call your sentence, even though internally it may have many sentences.
Sure.
There. And you know what? Because you're doing brute force chunking, you'll probably chunk in the middle of some sentence, right? Or even in the middle of some word. So that's all right. Yes.
So the 768 number, is that the number of the size of the chunk in this example?
No. The size of the chunk doesn't matter. It's the vector space in which target space in which you're embedding it. Right. So remember, guys, I want to say this quite strongly. See, here is the box, magic box, right? This is your f dot, magic function. It does not matter. It simply does not matter what the size of your chunk is. You can give a small text, you can give a big text, you can give medium text, you can give a ginormous text. Irrespective of that, the encoder, the function has decided what vector space it's going to put it in. In this particular case, it decided 768 dimensional vector space. So you say that the output, the hidden vector, belongs to an Euclidean space of dimension d is equal to 768. And the input text size doesn't matter. Everything, it will put it there.
So who's this? Who decided it was 768?
We can look up the name of the guy who made the model, but generally these are very respected research groups. This one maybe Google it. Yeah. See, it makes common sense. There's 512, 2 to the power something, and then there is 2 to the power 9, I believe, is 512, 2 to the power 10 is 1024. Split it midways. Somebody thought it's a good idea. Yeah.
Something 16 times 3 is 48, or 16 times 48 is 768.
Yeah.
Is there some numbers related to that? Or?
Yeah. I mean, see, here's the thing. If the way it never is that deep, usually in our community, right? People will start with something, they'll hack it. They'll say, oh, 512 looks, it's not working so well. 1024 is also maybe too big. Yeah. So let's split the difference and sit somewhere in between. That's how it goes.
Yeah, 512 plus 256 is 768.
Yeah.
Just for the sake of conversation. So let's say I took a sentence, just one word.
Yes.
Literally one word.
Yeah.
So word.
Yeah.
Right? And I'm just projecting it.
It will still be 768.
768. But what the values, is the values are going to be the same on all the 768?
No. Absolutely not. How can it be? See, look at it. You're projecting into a space, even in 2 dimensions. Suppose that word, horse, landed here. Look at its X and Y coordinates. It cannot be the same, right? There's no reason for for that point to land, right, at a place. See, to land at a place where X and Y values are the same is to insist that it is along a diagonal plane, a diagonal line. Why should it be? It isn't. It isn't like that. There's no reason for it to be like that. Are you getting it? Yeah. So, all right, guys, are we clear? So, input text size doesn't matter.
Quick question.
Yeah, go ahead.
So, is a 768 number depending on the maximum chunk size that it can take enough details into these dimensions?
No.
Is there anything like that?
No. This has to do with the nature of the model. This model, because it was using a BERT model, the maximum size of the input, I believe, is 500 tokens or 512 tokens. So the first generation models that came out, that was their capacity. Right? You could not feed it more than 512 tokens. Nowadays, the token length has increased, right? But that was the token length for the first generation models, input token length.
The 768, but 768 is still a magic number for that model.
It's a magic number. See, guys, as you develop more and more intuition about latent spaces and vectors in that, what will happen is you're just entering the field. But when you see lots of use cases, you will begin to develop some sort of intuition of what space is about the right size for a problem. It comes through experience. So it's not quite a magic number. It's not somebody pulling it out of his hat, but it is somebody pulling it out of his hat, but with some intuition, some experience behind it of lots of use cases.
Thank you. Each number in this matrix is a floating point, is it?
It's a floating point, yes. Everything is decimals, yeah.
So there's a variation over there also.
Yeah, there is a
go from negative very large number to a positive very large number. Right?
Yes, and let us look at that. Look at that. If you now wonder what exactly would this, so I'll take this poem, the famous poem that I presume many of you, those of you who know probably love it. Can you tell where it's coming from? Yeah, this is the Jabberwocky poem. Right? He wrote a poem in which not a word made sense, and yet the whole of it seemed to make sense. If you read a sentence, do you notice that none of the sentences make sense? Right? And yet, if you just listen to it half attentively, the whole thing looks like a wonderful story being told. So, anyway, so you want to see what does this text become? I hope it is obvious that it becomes these values. Now, I'm kidding. Do you notice that the latent vectors, the embedding vectors that it becomes, how many entries will I see in this vector? 760. It goes on and on and on and on and on and on. And there goes interpret. Do you think you have, can you look at this number, any one of you, and say, that's the Jabberwocky point? Right? There's no chance that you can do. Yeah.
So Asif, are these using the SHA-256 or something like that to convert all these text into?
No cryptographic. Guys, remember, there's no hashing. It's the opposite of it. You don't want to lose meaning. You want to capture the essence of a text. You use machine learning to understand, recapture human understanding of that text. Yeah, so you have a question.
How big are these individual numbers?
Oh, you look at it. 2.1, yeah, for example, this number here, for all of this, 0.5, 5.3 into 10 to the minus 1 is what? 0.53. So all of these are decimals. Almost
and
all.
There's no constraints on how big or how small they can be.
Yeah, that's a very good question you asked. Is there a constraint on how big and how small they can be? Theoretically, there isn't. In practice, machine learning works best with numbers that are not too far from the interval 0 to 1 or minus 1 to 1. Right?
Loss function.
Yeah, because what happens is that the loss function, instabilities come in when you deal with things way beyond it. So somebody nicely joked once that all of the neural networks or machine learning is done in a unit sphere. All the values are somewhere in there. Yeah. So, yeah.
So, I just want to clarify my understanding. The model has already been trained that we're using,
Yes.
and we're
Yes.
taking the sentence, which is
Yes.
that collection of all those words together. So the Jabberwocky, that is a full sentence. And based
Yes.
on that trained model, that is
Yes.
the position of that sentence.
Yes.
That individual sentence. And we have 16 sentences. So we're going to get 16 positions of
Yes.
those sentences, and then we'll use that to understand similarity between them.
Yes. So
Okay.
we just created a small search engine for which the whole world is just 16 sentences. And let's see if it works at all or not. And I just put a question there. I said a friendship with animals. Now observe something. Animal is a noun, but is friendship a thing? Is that you can? It's not. It's a little hard to quantify, right? And yet, now observe the search results that came in. I'm showing you the top 3 search results from the 16 things there. What does it say? I completely agree with this first search result. Golden retrievers are not bred to be guard dogs, and considering the size of their hearts and their irrepressible joy and life, they are less likely to bite than to bark, less likely to bark than to lick a hand in greeting. In spite of their size, they think they are lap dogs. And in spite of being dogs, they think they are also human, and nearly every human they meet is judged to have the potential to be a boon companion who might at any moment cry, "Let's go," and lead them on a great adventure. So when you read this sentence, what can you tell about the author of the sentence? What can you tell about the author of the sentence? Loves dogs, right? Has a very deep affinity or friendship with dogs, isn't it? But do you notice that the word friendship is nowhere in this text? Animal is, I don't think the word animal either is in this text. And do you realize what a feat it accomplished? Right in the very first example that I gave you, a toy example. What a feat it has accomplished. It has understood the spirit of the sentence, and it understands the spirit of the text that you have given. Not verbatim, but what is there, the semantics behind it.
I'll ask you one question here. So this response is based on just the input 16 sentences?
Just those 16 sentences. One of them was this, right? And it latched onto it and said, "This is it."
Oh.
Wow, that's what I wanted to hear. It's just absolutely amazing. The first time you see AI search, you're just blown away and you're saying, "What?"
Did any of your 16 have something about
No, it's the text
It's
is
there.
there.
Text is there.
Text is there.
But from
Text
the
is there.
prompt itself, there is no like.
No reference to that text. Right? I said a friendship with animals.
Exact match to
Yeah,
the
exactly.
search,
There's no
right?
like there's nothing like.
There is no exact match.
Or
Or even the
keywords in that
keywords.
string are
Even
not
the
also
keywords
there.
are not there. Right? So do you see, guys, I pulled off a feat with this that no keyword-based search, no traditional search engine could have pulled off.
So this didn't use, again, the gentleman who just spoke, sorry, I think Sarah said that we're using a trained model. So it's not using some knowledge that it already has and then we are building on top of it.
No,
It's just these 16 sentences.
there's 16 sentences, exactly. But it has learned, it knows how to understand human language. Right?
Yeah,
So
the key thing is that the model is an output of training. So when they went to build the model, they trained it to get some relative correlation to get our location, the 768 dimensions, and they trained it well enough and tested it that they had enough confidence that says this is a good model. And it's good enough that if we pass in 16 sentences, it can produce wow.
But the thing is, the word model is not getting knowledge from the 16th sentence. It already has something.
Yeah.
Using it.
Go ahead.
So, I mean, I would expect that one out of the 16 sentences is output, but it actually break down that one of the documents and then give the.
No. In this particular case, I just gave very short documents, very short things. So these are actually from the searches. Right? Look at the second one. If you're lucky, so guys, look at this. If you're lucky, a golden retriever will come into your life, steal your heart, and change everything. Certainly true. Right? Now, you notice again, there is no keyword match to a friendship with animals. You see that?
So is it mixing two sentences up and giving that?
No, it is looking at the meaning of it. And that's why it's called semantic search. Semantic and meaning are the same thing, similar things. It's saying, I am searching based on the meaning of this, which other sentences are closest to it in meaning.
But it's not changing those sentences.
No, it's not. Right? And likewise, if a man aspires towards a righteous life, his first act of abstinence is from injury to animal. I think this is Mark Twain. Right? So do you notice that a friendship with animals and injury to animals are antipodals, right? They are opposites. And so it latched on to them. Because if it says, well, injury to animals, right? And it says abstinence from injury to animals. Right? So, but now let's do something better.
So Asif, a quick question or a quick observation there, right? If we had gone keyword, your search rank, the last sentence probably would have come on top because the word animal was there and it would have picked up.
Exactly. Absolutely. You're absolutely right. It would have. And I invite you to take the same 16 sentences, try a traditional search engine and see what the differences are between this. And guys, what you're looking at, the first time you look at it, the first time I read the paper, it's 2018, summer. You know, you're looking at a revolution when you look at things like this. Right? And it has been. Today, words like vector databases, RAG, etc., are thrown around like tea and coffee or breakfast conversations these days. And we are learning that technology. Go ahead, Ranki.
For training 16 sentences, what are the negative?
We are not training. Remember, we are in inference mode. We have downloaded a trained model which knows how to extract meaning from text, meaning from sentences. In other words, it has semantically trained. How did we semantically train? Would somebody like to better recollection? Using what kind of laws? Contrastive laws, triplet. So you take sentences that are similar and one sentence that's dissimilar, you create triplets, and then you train a machine. And those triplets can belong to any field of human knowledge. And you just basically are teaching it to how do humans communicate. You realize that, right? You're teaching it the meaning behind gibberish.
Basically, you're feeding the text to the trained model.
Yeah. And at this moment, we take that model and now we are in the inference mode. We are saying, okay, we got a good model. Now let's feed it an input. It will make a prediction. It will give us a vector. Go ahead.
So say I want to build one American near accent, like near accent in USA, and then I want to mix to a Western accent and a Eastern accent all together. And then like, is that something that can come out with a new accent?
That's a lovely question. Just for fun, would you mind if I hold it down to 10th week?
Oh, okay.
Why don't we do the lab and find out? We'll do it. We'll do something. Right? And it will literally be a good, because I don't want to let the cat out of the bag. Right? So now here's something that you wouldn't imagine being able to do. Yeah, go ahead.
But does it really matter on the sense of vectors are related certain reason?
Yes. Also, the question of language and multilinguality. See, what happens is some models are trained only on one language, and some models are trained on many languages, multilingual, 40 languages. No, they don't have the models that are trained on multilingual. You can ask a question in English and get Tamil text, for example. I'll give you an example. Actually, this is very real. In the previous bootcamp, one of the lovely projects done by a gentleman, very, very bright mind, Sushinder, who is expert on Wi-Fi, he did. He comes from Tamil heritage. Right? And there are this lovely two-liners. These are called Tirukkurals. Deep wisdom. Anything that happens to you in life, there is a Tirukkural there for therapy. Right? It will really help you. It is no wonder that there are no therapists in Tamil Nadu, because you don't need them. Tirukkurals are there. So what he did is he found that they are not good. That wisdom is locked in there in the culture. He wanted to democratize that. So what he did is, and this was, by the way, he did it really after the first lab itself. He took the Tirukkurals, he created a sentence embedding of it, and the query would go in English, and what would come back in response? The appropriate Tirukkurals. And I believe his website is literally called Kurals or Kural.com or something like that, Kural.ai or something. He created that and he made it available as a service, and it's lovely. And then he also uses another part of AI to translate it into English or into any language of your choice. Right? So guys, this is the power of these things. People in previous batches have done wonderful things with just the first lab itself. I hope in this batch too, I see something that will surprise us presently.
So also can just scroll up the query.
Okay. Here's the query: our friendship with animals. Now you realize how powerful this engine is, isn't it? Right? Now, here's the second part of the query. I don't give it a text at all. Okay, hang on. I'll come to more questions, but let me finish it, guys. I'm getting. Oh no, ask it. Okay, Sanjeev, go ahead.
So while training the model, essentially, they have fed enough data to plot the vector and they store it. And then when I'm giving the sentence, then they're plotting and finding the angle.
Remember, no, stop right there. Sanjeev, they have not trained the machine to store vectors. They have trained the machines to produce appropriate vectors. That's all. The machine is stateless. It doesn't remember anything. You give it a text, it will just produce a vector and give it back to you, not store it, that it thinks is appropriate. In that embedding space, it will give you a meaningful vector. That's all. That's all it does.
So how it will search? I'm not able to understand. So I gave my query, which is essentially a vector.
Yes.
So some form of mathematics, right? So I need to find something that's close to. In this case, the golden retriever is whatever, right? So how it's going to compare
the way it works is that this particular library has given a little utility. It says that if you want to just do toy examples, we can hold some of your text in memory and search and produce the results. So what it does is you give it 16 sentences. It converted all the 16 sentences into vectors. That part is easy, using the transformer. Then you give it a query vector. the query text became a vector, and then it went and compared it against the 16 vectors and found out what were the 3 nearest neighbors.
Okay.
You're saying there is not even a model used there?
Well, your model is there. Now, how would you get vectors out of text?
But then just to be sure, this query text
Yeah.
was only compared with the 16 times
That's it.
768.
No, just 16 text, the vectors associated with 16 text.
Correct. So it did that comparison.
That is it. That's all.
But the model is trained to generate those 768 numbers.
Dimensional
for each
vectors
sentence.
for each text. Yeah.
Sorry. Sorry, go ahead. So, the model,
Mhm.
what we use to embed the sentences
Yeah.
and for the query, you gotta use the same model? Or I
Yes.
can use
You
a
must.
different model?
No. Very
Because
good
that-
question. You can't change that because every model has its own way of thinking about semantics.
Creating vectors.
Vectors, yeah. So you can't mix the model midstream. In fact, that is the most common bug you have with developers.
Yeah.
They will say, search results are coming out very bad. Why? They will run up and down. Data is corrupted. No. And then it would turn out that a completely different model was used to create the vectors, and a different model is being used to.
So, even not only text, even the audio also we can produce.
Absolutely.
Say like the Indian Prime Minister.
Yes.
Recently, he was speaking in Hindi.
Yeah.
But it was converted into many languages simultaneously.
Yeah. You'll develop some of those abilities in this workshop.
Yeah.
You guys, we are just making baby steps. Go ahead.
The model that was used to create these vectors.
Yeah.
When it was being trained, right?
Remember with the triplet loss, it was fed a lot of web content, converted into triplets, and then trained on it.
Yeah. So and then you have to supervise it, right? Like saying, hey,
What do you mean?
supervise
No, the moment you put a loss function on the output, that's the definition of supervised learning.
Sorry,
Go
I
ahead.
got lost a little bit. So the model was trained. Then we had these 16 sentences with 768 vectors. I thought the model was trained on those.
No. Let me get this right. Guys, we have downloaded a pre-trained model. How is that pre-trained model trained? By taking lots of content off the internet, converting them into triplets, two guys similar, one dissimilar, right? And then using a triplet loss mathematical function, it was trained, that whole neural network was trained. And that entire neural network became one function. It takes text in of arbitrary length, but it produces a vector of a fixed length. What length? 768. Now that pre-trained model has been hosted on the internet. You just downloaded the model. Now this model is ready to use. It understands English. You give it a text, you give it a query, you give it some text, 16 text. It will produce vectors. You hold on to the vectors. Now you give it a query, it will become a vector. Now, vector comparisons are easy. We just talked about cosine similarity, right? You just do cosine similarity or dot similarity, and you figure out which are the closest vectors to that. Very well.
But where is the 16, that matrix of 16 vector, 16 sentences, where does that figure in? Because the model has been trained on hundreds and thousands of vectors.
Okay. I suppose we are getting so confused. Let me write it out for you guys. Yeah. See, give me a second, huh? I need to bring up the writing pad and start writing.
Well, one of the ahas that I have is that we're not building the magic function. We're simply using the tools that others have already built to understand how to work with this portion of artificial intelligence. And once that made sense in my mind, I'm like, oh, this is what already exists, and I'm gaining familiarity with how to use it.
That is right. That is right, sir. See, remember, this is the first section of the bootcamp. Let's learn to crawl before we walk and run. Right? So we will build our models, we will train our models, but that is way, way off. Let's start using other people's models.
Awesome.
Guys, here's the thing. A lot of you have questions, but all the questions are like when I'm answering it, I find that I'm just repeating myself over and over again. So what I would like to do is explain it one more time from scratch. Hold on to your questions. Let me explain, and then we'll take more questions. Right? So guys, here it is. There are two worlds. One world, one thing, and let us call it, let me just call it, this is 2022, just for the sake of argument. This is today. This is the world when we train the model, just hypothetically, when we train the model. This is the day when we download the model, load the trained model. So how do we train the model? Let me recap it for you guys. You take this box, you give it, remember the triplets. What were the triplets? A good data, a text A, text, similar text to A, and a random text. So if you give it 3 texts, this is a box that takes any X and produces a hidden state, a vector. Are we together?
Yeah.
This, now we agree, let's take this particular lab. This vector belongs to 768 dimensions. So this is called a triplet. So what will it do? It will go and project TA, let's say, becomes HA, the hidden state, the hidden vector for A, latent vector for A text. A TS, let's say, lands somewhere else. TS lands the hidden state for S text, lands here. And let's say that HR lands here. Now you say, well, that's disappointing. I don't think you've really understood English about how we speak. So what you need to do is, we are telling you these two are similar and these two are dissimilar. So hold on, all of you hold on to your questions now, right? So what you want to do is, would you not, when you're training, what would you tell this guy if it was a child? You would say, try to place these two closer to each other and try to place these two farther from each other, because at this moment they seem to be at the same distance from A, isn't it? Guys, look at this, which are more or less the same distance from A, right? So you're saying you haven't quite gotten it yet. Next time around, do better, right? So what you are doing is, let's see how you, now mathematics is nothing but common sense written large. You want to minimize the distance between HA and HS. Would you agree? Right? And you want to maximize the distance between HA and HR. Do we agree, guys? Right? And to maximize this distance is the same as to minimize the negative of this distance. Right? So that's that, right? So we can say that the loss for this data item, this triplet I, the loss associated with just the ith term, ith example, you call it an exemplar or exemplar triplet, is equal to, like, what you want to do is minimize the distance. So you want to, like, you take the distance between HA. This is the intuition, guys. Huh? The mathematics is a little bit more intricate. Minus D, HA, HR. And I can write the loss. If you think about it, the smaller this quantity is, the more your model has learned, isn't it? So suppose your model next time around produces these points. Let's take this. HA, HS, HA is here, and HR. What do you say? Do you think the model has learned something about your language, the semantics of your language? It has. And so this distance is minimum. This distance is negative. Again, there's a negative. Big distance, but negative. So your loss has reduced. The loss term is called the loss term. Loss term has reduced, isn't it? So what you do is, in one epoch, and this is where you guys need to come to the theory part. So in one epoch, one cycle through the whole data, you're cycling through millions of rows of millions of triplets. You accumulate all of this to get the total loss, and then you say minimize loss, minimize the loss. So you're basically saying that, see, at any given moment, the model has its own state. These are called weights and biases, right? And so, let me give you an intuition. Have you ever been to for example, if you go to a grocery store where they have a scale, and especially in an Indian grocery store, if you try to buy sweets and say 1 pound, they'll add something, and then they say, oh, it's too much. Then they'll break something apart and take it away, right? Things like that. So think of it, these weights sitting in the machine has lots of knobs. Okay, think of it like that, lots of knobs. And all of those knobs help define a function, right? Every time those knobs turn, the function changes. It's a different mathematical function. What are you looking for? You're looking for the perfect function that is usually in our field represented with a star. The star function, which minimizes the loss. Are we together? So you do that. And when you have done that and burned through enormous amount of electricity, as Prashant would point out, right? Then you say, we are done. 2 weeks of training on this big machine, like literally something like that. And now I have an asset. What is that asset? A sentence transformer. These things are called sentence transformer. So this is part of the culture of this field. See, when people created this, Google was one of the leaders in this space, they could have decided to just keep it in-house, right? But research community has a way sharing that knowledge and progress should be shared. And to its credit, they shared the model. They made it available. And today, if you go to Hugging Face, that's one of the things we'll do in the next lab. We are going to explore Hugging Face. There are thousands, tens of thousands, or hundreds of thousands of models that people have trained and put there, right? Some of them are foundational models. Some models are taken by taking somebody's model and doing some tuning to it, right? So you have a general model and you fine-tune it for your legal domain or something like that. And then you share it with other people in the domain, in that vertical. So, but the foundational models, right, are all there.
So what is the difference between a foundational model and the generic model or other specific models?
See, the foundational models are those models generally which have been trained from scratch with data. You take a neural network with all the knobs are in array, random, and then you start training it from there. And generally, foundational models also have the quality that they're general purpose. They can solve a whole variety of problems. Are we together? They solve a variety of problems with quite good performance. Right? They are versatile and they have been pre-trained on a lot of data.
Is anyone on the call or can you hear me?
Yeah, I can hear you. It just died for me. I was
Okay,
just
so
about
we
to
lost
chat.
Asif, right?
Yeah, I was just about to chat. Like,
Asif's
I
call
mean,
frozen.
I can hear you too.
yeah,
Yeah, Asif froze.
yeah, there we go. And he's gone.
Okay.
Just when I was about to get it. No, just kidding.
You got.
Are you
You
guys
got time.
seeing? Am I back?
Yes.
And
Yep.
am I sharing my screen? No.
I think everyone's.
All right, guys. So once the model is trained, what does it know? If you ask yourself this question, what does this model understand? What does it understand? It understands language, isn't it? It understands the meaning of text. That's all it does. Universally, it understands language. So when it produces a vector, hold on to all your questions, guys. I know lots of them are there, but give me 2 more minutes. When it produces a vector, it is producing it based on that understanding. Now comes the other world. So that was 2022 then. Like, let's say that's when you train the model hypothetically. Today, what are you doing? This world is inference time. Now, use time. Let me call it the use time or inference time. At inference time, what would you do? You would say, model has been trained. Let me go get it. I got the model. I fed 16 sentences into it. 1, 2, text, 1, text, 16. What did I end up with? 16 vectors, right? H1 all the way to 16. We got that? Are we together? And now what can we do? We can do something very simple. We can take the query vector. Okay, we can take the query vector, the text, query text, make it into, we can pass it through the same system, pass it through the same machine, and what it will come out with, the query vector, isn't it? It's just a vector, just like other 16 vectors. Now vectors, I can find its neighbors, isn't it? And suppose I pick the 3 nearest neighbors, semantically, they have to make sense, isn't it? So that's what we are doing here. That's all we are doing here. Is it clearer? A little clearer now?
Asif, can I ask a question now?
Okay, yeah. Okay, now let me take questions. Go ahead.
Yeah. So your text that had 16 sentences basically is, as you said, it's a garbage, right? It has nothing into it. Now you can give any
No. Hang on. I don't quite follow when you say nothing onto it. These are lovely pieces of human literature.
No. That is okay. But with respect to the query was and the friendship is love. What was the query? Friendship is animal, something like that.
Friendship with animals.
Yeah. So that thing, like now, okay, you have a pre-trained model on all the web. You cleared with that. We downloaded that model. Now we have our own data that we are training on that model. Now, our trained data has nothing on the animals here.
No, stop there. That's where I want to take you. There is no such thing as trained data. Models get trained. Data is inert. It's done. It's data.
Yeah, we are training the model with the new little data, the 16
No,
data.
training it. We are not training it. We are feeding it to the model. See what? So here's the thing, guys. Shraddha, let me just mention. See, once you have trained a model, all the weights. So what happens during training? We were calibrating the weights, isn't it?
Mm-hmm.
And so, like you see that, when you do it with a balance with 2 pans, there's a kilo here, and then you put enough amounts of potatoes. Now this pile of potato becomes a kilo. But now imagine that you're done. This pile of potato is frozen. You're not going to add more to it or take away from it. This is your frozen thing. So when you download a model, all the weights and biases, the internals, are frozen forever. Unless you unfreeze them. You have a choice to unfreeze them and further train it, but by default, they're frozen. No, you don't.
No, Asif, I agree with it, but any ML application that I have worked with, you have a pre-trained model which is just trained on a lot of data. Now, when you start your work, you have a particular data or a particular corpus on which you start working on. Or in case of computer vision, it would be new set of images that you want your model to be trained, and then you give it a query, and then it gives you the best answer. So in this case, your results are 0.24 or 0.28, the query search results. That's why it is putting in 1, 2, and 3 steps. Because the general question that I have is, here your corpus that you gave is not linked to the query much. It's not like the corpus and the query are not very similar. That's why our score is very poor.
No, actually, those scores are not poor. They're pretty good. Those numbers usually come out very small. Now, so see, Shraddha, I understand where you're coming from, but you're mixing two things.
Yeah.
See, you said that wherever you work, you further train the model.
Yeah.
The that is fine tuning. Further training a model, a pre-trained model is fine tuning. You have a choice. when you get a pre-trained model, you have to ask this question: is it good enough for me? Or do I need to further fine-tune the model? Right? At this particular moment, when you don't fine-tune it anymore, when you use the model in practice at runtime, give it a query, get a vector out. That is called inference. You're inferencing from the model. Are we together? When you're inferencing from the model is frozen. You're not touching its weights and biases. At this moment, what are we doing? Are we inferencing or further fine-tuning the model? Inferencing. We are purely in the inferencing mode.
Then what is the purpose of your corpus there? The one that you provided 16 sentences. The model,
Suppose your company has, or on your machine, suppose you have a company has something, it's a documentation, user documentation. Let's say that you manufacture something, a fan or a tool. And to help your consumers, your website contains vast quantities of documentation. It tells you if this tool breaks down this way, do this. If the tool breaks down that way, do that. Right? This is the right way to use it and so forth. Vast quantities of information are there. Imagine if I could take all the document and make each of those into, and break it up into chunks and make them into vector. Now, in this scenario, on your customer help portal, customer service portal, imagine that the users could come and ask questions. How do I fix this? Or something has happened. Do you realize that this would find the semantically most relevant answers? And that is an example of its utility. Basically, Shraddha, every single use case where you can use a search engine, this is useful. If you think about it, that's what all search engines are. They shred the document and store some internal representation. In the keyword search, it's an inverted index. And then a query comes and then you search for it. Search for matches. And the utility of search engines are undeniable. Okay, guys, lots of questions. I don't know in which order to go.
So the T16 which you gave, the query, if you gave like something, you trained this, or the T1 to T16 is the same thing.
Yeah.
But query, say you ask something legal or medical thing, what would happen?
So what it would do is, because you're looking for it would produce a vector. The AI will produce a vector. Then you are now comparing that vector to all your 16 vectors and saying which is close. Some random one will be close, but you would know by looking at how close it is, that it's not really that close.
So basically the T1 to T16 is in a sort,
your search space. It is the search space, and you're allowed to search.
Narrows down the search space from the big database of.
No, you have a database of only 16 text.
No, the pre-trained model.
Oh, that it has forgotten. Remember, a model doesn't remember what it was pre-trained on. It doesn't store it.
So you're using the model to find your data.
You just have that F function, that's space. You just have that F function, and this
exactly.
16 will go into some space, right? Vector spaces. And
that's right.
So
this is it.
Let's say TA is I love cat.
I love cat.
Okay. TS is I love dog.
Yeah.
Okay. And the TR random is I butchered a chicken.
Oh, hopefully not.
Right? Yeah. So now I understood how the answer was coming. But what I'm trying to comprehend here is, okay, you said you are bringing TS and TA closer, or you're telling the training during training that bring TS and TA together.
Exactly.
But please put TA and TR far away.
Yeah.
So
that's it.
What is saying that?
What is doing that? So you do it. The way to telling it is the loss function.
So is it automatically generated?
No.
Function or
loss function is you, the mathematician. Okay. The mathematician who writes the loss function. So there is a whole theory of contrastive loss, and you're harnessing the theory of contrastive loss, and then the process of learning is the standard gradient descent.
But when there are zillions of lines from which this model is being trained,
Yeah.
how are we writing that loss function to say I love cat and I love
No,
dog?
it doesn't do that. All it is saying is I'm getting a triplet, right? A TA, TS, TR. So it will always get a triplet. The loss mathematics ignores what the text is. All it says is that the vectors that get produced need to come together.
Yeah. So
That's
and the mathematician is somehow
Yes, and for no, not somehow. That person happens to have taken my Tuesday machine learning class.
Asif, again, Asif, I'm sorry to jump in there, right? But I see, like, there's still a lot more confusion and that goes in circles. But if we talk in terms of, let's say, ChatGPT, somebody did the training on ChatGPT to produce the loss function and all that using billions of those triplets, and that produced the large language model.
No. See, there are many algorithms in machine learning. This one that I'm talking about, triplet loss, is only meant for sentence. I mean, it's very useful for sentence embedding and some other use cases. The GPT has been trained in a slightly different way. Actually, in some sense, we will do the GPT architecture, but hold out on that. It's a different idea and a different architecture.
So coming back to that Shraddha's question, so even the current GPT-4 or whatever, right? So whatever information we're trying to get information, but indirectly it is at the background it is getting trained further actually.
No, it doesn't. Once you freeze the weights at inference time, it doesn't learn. In fact, you don't want it to learn.
Actually, the YouTube video that I was referring,
yeah,
so he was saying like basically don't type something about your manager or is this that.
Yeah, Prashant mentioned something that don't type something about your manager, etc. Like the advice that's given.
And suddenly it will come back again in smaller form.
The reason for that is because ChatGPT and this public things, what they do is every text that you put, the reason they make it free, when something is free for you, you are the product.
Yeah.
Right. So what they are doing is you are the guinea pigs feeding it data that they will use for the next round of training.
Yes.
Right. And so it is the next time it gets retrained, they'll use it. Yes.
So in this case,
I'm sorry. Right?
Hey, Anand, please hold on. I have a question in the audience here. Go ahead.
In this case, we trained the model in 2022, right?
Yeah.
And then we have a sentence transformer, which is trained. What is it actually? Is it just the algorithm or it comes with some kind of learning?
No, it is not. Very good question. So the question is, what exactly is this transformer when we download? It is, see what happens is, it just tells you the knob values, the weights and biases. That is nothing but these AI models that are changing the world are nothing but giant matrices of floating point numbers. It just says this neuron, these are the weights, these neurons, these are the weights and biases. That is all you download.
So just in this example, right? T1 is getting, you have this function, it's getting saved as a triplet somewhere in the reference space.
No, it's just a no. See, this is for the training purpose, right? This is gone. When we bring in, our world is this world, the one on the left, on the right. Our world is this. When you give it a text, it will produce a vector.
But these vectors are just in this one in triplet?
No, not triplet. Just a vector. Just a vector.
Okay, just a vector.
Just a vector.
So which class of yours teaches how to write loss functions? Tuesday class?
Tuesday class.
Asif, I think the confusion is that the input is also your search space. Right, those 16 sentences also needs to be fed into this. I think that's where everyone
that is it. Okay, guys, let me break it down to pieces. How did this work? A T1 went in, it became H1, right? Then somebody took it and put it in the space. It just put it in a bag, put it in a box. I say I have a vector H1. Then H2 came, H3 came, H16 came.
Yeah.
Right. Then you took the query and it became the query vector. And then once you get the query vector, you go into this bag and find the neighbors. The model is not doing that. Model is just producing the vector for you. Right? Someone else, I mean, it's just basic neighbor search. You do the neighbor search and you find which of it does it match most. That's all. Is that making it clear now?
So just a quick follow-up on that.
Yeah.
So if we put a different set of 16
hold
and put text.
I think Anand is waiting for the question. Anand, go ahead.
No issues, Asif. I was just going to say from an analogy perspective, right? It goes whether it's different architecture doesn't matter. Where I was simply going was, look, the 16 becomes your universe against which you're feeding the query. Similar to how I would do it in GPT, right? I would say, hey, here is some information that I'm feeding you. Based on this, give me something, right? That's essentially what we are doing here, right?
That is, in a way, see, Anand, in this case, right, it looks as though, let me just put it this way. I'll put a wall here. This wall. You see this yellow line here? To the left of the yellow line is just this model that converts a text to a vector. And it does nothing else. It doesn't know anything. It doesn't remember. It doesn't store. It doesn't speak. It just says text in, vector out. It's a function. Functions are structures. Now we happen to have stored those 16 vectors and deliberately compared. These are we did that. The model didn't do that. We did that. We said, okay, let's take the query vector and compare it against only these 16 pieces of text and find which ones are the closest. We did that.
So essentially, it's two sets of programs running, right? The first one was the model doing the vector conversion.
Yes.
The second one was somebody wrote a utility on top of it saying, hey, I'm going to feed you something, create vectors, and then I'm going to give you a query text, compare it to the vectors that I have created and get me the closest ones.
Exactly. That is literally the utility. And that's why I said, right? I pointed out the library starts with a
And as if the first thing that the previous person said, when you run the model and then you're you are having a utility function on top of that, and your pre-trained model is helping to give you the most precise vectors. That is the purpose of pre-trained model.
No, the pre-trained model just gives you the most semantically meaningful vectors. That's all. It will say, give me text, I'll give you a good, nice vector that I believe that reflects it.
Right, and that is coming from the choice of how good you use the pre-trained model or the and finally it is the model that is predicting the semantic similar vectors, and then it is the utility function that is just
yes, that is utility function. See, here's the thing, guys. Models are stateless. They produce things and you're done with it. You happen to have saved your 16 text as 16 vectors and you're comparing against it. In fact, and let me use this as occasion, the saving of those vectors is called vector database and searching into it. That's all. Let me color it differently. Do you realize how simple these ideas are? This thing, now you're coupling the model to a vector database. We just searched in a very, very, very simple vector database in which we had stored only 16 items, and given a query vector, we found who the neighbors are. Right? So is it now making a bit more sense?
Yeah.
So question on that.
Yes.
Is the vector database what it learned based on the model?
No, vector databases are not intelligent. They're dumb things. There's no AI there.
So
where would you apply? Is learning applicable here?
Yeah, so I'll give you an example. See, the vector database or approximate nearest neighbor search or vector stores, they have been around for decades, right? And they have been getting better and better and better. And the reason they are getting so much attention these days is simply because we can do more powerful things. We have use cases that harness them more. And that use case, for example, is sentence birth, like the sentence embedding. Right? You can create.
Sorry. Just a quick question, right? Like, so if I understand it right, like there is a training that has happened over hundreds of thousands of lines. And based off of the meanings of those things, the creators created a loss function which puts similar words together, right? And then he knows the bias and all the things that's needed to put those words together. And then he gave that loss function to as a trained model, basically. And then you use that same trained model and then you pass in the same different set of words. It knows how to put those words together. That's it.
Absolutely, absolutely. So guys, get used to using this vocabulary that we use in this field. You are inferencing with the model.
Exactly.
We are inferencing with the trained model. When you inference, and try to use these words, when you inference with a trained model, the model doesn't mutate, it doesn't change. Its weights and biases are frozen. People use the word frozen. Its weights and biases, its internals are frozen.
So as if again in this example, it's becoming clear to me, but I just want to confirm it with you. If we give it a different set of 16 sentences,
yeah,
then the output would be different.
Different, of course, because you're comparing against a database of what you gave.
Sure.
Yeah, and in the word of natural language processing, whenever you hear the word corpus,
yeah,
it's synonymous with
with
database.
So you used the word lawyer earlier. If the query was the lawyer's sailboat,
yeah,
you probably get something fairly nonsensical.
Fairly nonsensical.
Because the input text did not relate to that.
Is not related. Absolutely. Okay, guys, is it getting a bit clear? Oh, more questions. Go ahead.
How do you know what to populate in the vector database?
Oh, that practical reality does, right? For example, you want to create a customer service search for customer service items, documents. Go put all your help documents into the search index. Right? Practical reality dictates what you put in there.
It is a pre-trained model. It's so these vectors H1, H3, they are just randomly getting saved in the database.
Yeah.
It's not like right now it's not making a decision. It's this sentence is far away from this sentence.
That's
it's just getting saved.
Yeah, the vector database is smart in knowing how to save it. Yes. It may just keep it as a dumb list if it wants. But you don't care. So guys, are we now? Is it now making sense? Any more questions? You have one question.
So basically, is first creating the loss function.
Yes, no, that is training. That is training. Training the model. Loss function comes in only during training.
Or rather, creating the database.
Vector database has nothing to do with the model. It is just a way to store the vectors.
So the inference part first is creating the vector database and finding.
No, it's just producing vectors. You give it 16 text, it will give you 16 vectors. It doesn't care what you do with the vectors. You choose to put it in a list or somewhere, store it somewhere, which therefore is your vector database.
And then the second part is the nearest neighbor.
Yeah, that is it. And nearest neighbor algorithms have been there in computer science for as long as we can remember. So guys, is it making sense now? Anybody remote who would like to ask a question before we continue? Now does it make sense? Is there more clarity now? What's going on? Remember, there are two different worlds. Training a model, which is hard and needs a lot of mathematical understanding, and inferencing from it. Right? It's like somebody has manufactured a car. You just need to get in. So long as you know the steering, the wheel, and the brake and accelerator, you're fine. Right? So that's what we are doing. Now, and yet, I hope, guys, now you see the magic. See, these are very simple ideas of vector spaces and abstract ideas. But look at the profound implications of those ideas. Do you see that it can produce pretty good results? But here is a beautiful thing. I was coming to something which will again be powerful. Suppose instead of giving it a text, I gave it a picture. And I don't tell it what it is a picture of. To the machine, a picture is just a bunch of pixels, RGB values. It's an array of floating point numbers, isn't it? Right? Yeah. So, and you can see it if you ever store it in raw format. I'm storing it and I'm giving it just to giving it even a small search space. I'm saying here are 4 sentences, short sentences. Yeah. And let's see which one it matches out of the 4. Right? So what you do is you create vector embedding of the image and vector embedding of these 4 sentences, and you again do the nearest neighbor search. Right? So you can see there's an elephant there, there's a dog there, there's a golden retriever, and there's a furry dog. But elephant shouldn't come up, right? Attention is all you need, shouldn't come up, and a cat, God forbid, shouldn't come up. car on a highway shouldn't come up in the search results, right? And see what happens. I didn't give it text at all. And it picked up these results. It not only, first thing it latched onto is, it knows it's a golden retriever. Right? By the way, this species of dog, if you don't know, is a golden retriever, the best of them. Right? And sorry. And then the love of this furry, but notice the second search result. What does it say? It said, for the love of these furry dogs, the machine has understood that this dog is furry. Right? Isn't that amazing? Right? I mean, I don't know, guys, you look at this, you see, once you understand all of this, you literally see magic emerge from all of this. Right? And then the third one is a smiling dog, which also happens to be true, but it didn't come up with a car. It didn't come up with all the other nonsensical ones. Cat on the windowsill. Attention is all you need, or something like that. Right? So this.
So what's the post? Just go back and just look at that code snippet for a second. So okay. So again, we gave it the same sentence transformer.
Yeah.
This time we gave it the image.
Image.
And then from the image, this is able to derive this as fur, this is a dog.
And
is the model different?
No, yeah. In this case, when you do images, you have to load a different model.
But then it will get it onto the same vector space.
Vector space, yeah. So guys, these things will, like, I know that this is all very new and strange, but when you do the project, it will soon begin to make a lot of sense. It's time to do something, right? So I'll give you guys this Jupyter notebook, play with it. Now, there was another image, but I have to run this notebook and then I'll give you. You could instead give text as query and search through images. So I haven't downloaded these images because this is my teaching laptop, but it's on my server. You run this code, it will come down on your machine. So you all know the website Unsplash? Yeah. Unsplash is a public website from which you can download images, public images, for free. So this is a data set of 25,000 photos from Unsplash, right? Random photos of all sorts of bizarre things, right? And then when you search for it, and at this moment, I don't think on this machine those images exist, so it will show up. Yeah, but when you do that, let me see what is the prompt I gave. Now you index images. Most of your corpuses, I mean, your vectors are made out of, manufactured from images, isn't it? You give it a text query. Let's give it a text query. Where is the text query? To love a dog, right? You remember, it's the opposite. We're giving it text and saying find images. Do you think this machine can? Of course. And what you will find is, you will find pictures of not just a dog, but somebody actually in doing something to the dog that conveys that emotion, right? And it's very remarkable. I wish I could show you the picture, but let it be for you to run this and see the results.
Very basic question. So even in this transformer,
yeah,
that's looking at an image, you generate the same 768 dimension?
The dimensionality would be, I believe,
clip. Our dog would, when you put it, will give you 768, right? The image also give you 768?
Yeah. No, see, when you search, you have to search in the same vector space. So in other words, you have to use the same model that you used to vectorize.
Yeah.
That's all. So long as you use the same model, what dimensionality it was doesn't matter. Clip VIT-B32, you guys can check what is this dimensionality. I don't know, maybe 768, maybe something else. Right? Are we getting it, guys? And so I wish I could show you the image, but let it be a discovery for you when you run this, right? And what I will do now is I'll take you guys through the process of setting up your environment, make sure that you guys are all smooth with it. The next thing is, this is a search, house next to a lake. And what you would notice is that you gave it two words, house and lake. It could have come up with lots of random pictures of houses, lots of random pictures of lakes. But actually, it knows what you're looking for. And it literally finds beautiful pictures of houses next to lakes. And you have to see it. You can go tougher. You can say jumping dog. Now, jumping is an action, right? And sure enough, it comes up with pictures of not just dogs, but dogs that are jumping. Right? And likewise, a pathway through the forest, it won't just bring some path or some forest, but it will bring this beautiful trails that are going through the forest. Right? And you can play more and more with it. Right? I will post all of this on the Slack channel, and you can play with it. Guys, I will take field questions. Let me say something. So guys, I'll just summarize what we learned. What we learned is you can train a neural network, a neural architecture, transformer architecture, with the triplet laws such that it puts meaningfully similar things nearby, just similar things far away. That's what we got from it. Right? Now we are going to do a paper reading to do it more formally, carefully, that same argument. You'll see it. But you notice that the fact that you can train a machine to do that has practically, you wouldn't imagine that if you could do that, it would have such far-reaching implications, isn't it? You wouldn't typically think that it could do so much, right? And yet it can. Right? That is one. In fact, that's the foundation for semantic search. What you just did is semantic search. Now the question is, what happens to traditional search? It turns out that if you give sentences that are not semantically rich, that have very little information, then keyword search beats semantic search, right? So what people do is, you typically have a merge. You don't know what the user query will be, good or bad, rich or not, semantically rich or not. So you do keyword search, you do semantic search, you bring the results together, and then you use yet another AI model called a cross encoder, right, to re-rank it and see which is the best amongst these, and then produce it. Are we together? You re-rank it. So in reality, you do a much more complicated thing. But for today, see where we are, I would suggest that let's stick to just sentence birth, right? That is what we'll say. The other thing I want to say as closing is, remember the model that I'll explain to you at this moment was trained like in the beginning with just text. The question of how you can do this magic with images, you must have noticed the word clip in the model. A clip is actually takes this whole idea that we have been discussing much further, right? And extends it to images. Clip is an architecture. Again, we will use it, but for obvious reason, we won't cover it here because we have a lot of territory to cover here. Remember, this workshop is do, building things. The theory is on the other side. And it seems that you guys will all benefit a lot from the theory. So come by. Remember, 2 sessions are free. 2 more sessions are free. 3 sessions are free. So come by. And with those closing thoughts, I'll take questions. I think I saw 2 questions.
Yeah, Asif, can
Yes.
Yes. Can you quickly tell us how is a transformer works differently from any CNN model? Like very quickly, some things, because
Yeah.
When we talk about
In
transformer,
short, it has the concept of attention. Attention looks, see, a CNN has the receptive field is local, right? It has a local receptive field, but in a CNN, in a transformer, given a text, long piece of text, it still is able to pay attention to very distant words from each other, right? You have a concept of self-attention, which is the core underpinning of a transformer, but that will take a bit of time to explain. See, in very simple terms, it's like this. The cow jumped over the moon. Cow, and let me put it many other gibberish in between. The cow who had a good sleep jumped over the moon. What would happen is, suppose you have to translate this to French. You know that in French, the order of the words would be different. This word cow will pay attention to jumped much more attention to jumped in the moon, right? And far less attention to, let us say, had, right? So you pay differential attention, and it is the concept of attention that is the core driver, the core idea or intuition that makes the transformer architecture possible. So today people do hybridization of these. They hybridize transformers, attentions, CNNs, all of them in one big pot and create complex hybrid architectures. So that's going on. All right, any questions? I had two from the audience. Please go ahead here.
So for the content, the inference, do we need complex hardware or this laptop?
Oh, no. You don't need complex hardware. $1 million hardware is enough. No. For the early labs, you don't need any. Right? Only towards the very end, you will need hardware. We have hardware here. Each of these offices have hardware. I'll give you some level of access to this hardware. And Hamad, you have a question?
When it's going through a sentence, is it looking at every word as a weight? When you're saying that
every word as a
weight, is when you're saying that.
Yeah, attention is literally that. The word cow, how much weightage is putting to the word moon or the word, that is all it is.
That's every time it invents something.
No. See, hang on. Do not confuse this attention discussion with what I just explained. Let's not mix them up. I got a question, what is transformer, what is attention? I was explaining that. Just forget about this discussion.
So, inferencing, perhaps we're doing this large dot product, right? It may some hardware acceleration may help.
Oh, of course. Anytime you do dot products, you remember it's a quadratic thing.
Yeah.
Like it is that famous dot product inside attention that's making NVIDIA into $1 trillion company. Any more questions, guys? If not, we'll take a 10 minutes break. We'll do paper reading and we'll move forward. So guys, ask these questions. I want to make sure you don't have confusion. But are you in a state in which you broadly understand what we are talking about? Yes. And run the code. I'll help you set up your environment. But first, we'll do the paper reading and then do that. Hamad, don't worry about attention. That's a different topic. Because if you bring it, we're talking about something very deep. Whereas here I'm talking about sentence cross entropy loss. So
can we access the Jupyter doc that you shared?
Yes, I'm going to share it. Give me time. After the end of the lectures, I'll share all of it.
Maybe in Slack.
You need to talk. It's bad. It's really bad out there. So well, we have to get the root cause of this. Explain what's wrong with the disk, but that whole that entire driver that whole packet is corrupted. We tried everything to get it back. We tried recovering it, just even trying to see if we could like get the partition mounted again. That my drive is unrecoverable. It's supposed to fall installed.
I'm here.
And
Asif sir.
Okay, we'll worry.
I'm here.
Okay. Yeah, Sukhpal, why don't we take it up later? What is done is done. We'll worry about it and
no. So yeah, Hamad can sir. The Red Hat server is up and running, fresh install, and just need to install the Moodle and copy the data.
We'll do it. And I need to call up a professional recovery service to recover the data from the disk.
Yeah, so there is a clone and the actual disk right there on the desk.
Yeah. So the clone is there, right? We were able to successfully clone it, isn't it?
Yes,
and
clone. Yeah, that was.
What you're saying is that the actual disk is destroyed. Hamad came and told me the actual disk is destroyed.
Yeah. So yeah, data partition we try to recover it, but no.
We managed to overwrite it or something. It's okay. That's all right. I'll just send it to a professional recovery service.
Probably, yeah. So we don't have no backup of the website's code.
No, we don't have, Sukhpal. You have asked me so many times. We don't.
Codevector.io code nowhere. Okay.
All right.
Yeah, let Hamad separate the Wi-Fi and hardwire network, please. That's also cross-talking.
Asif, Your audio is still on. I don't know if you wanted this conversation over the group chat.
Oh, yeah. Thank you
Yes,
for-
yes, we know.
Okay, very good.
Sukhpal, let's really take this on. At this moment, I want to stay focused on this section.
Yeah, no problem.
You know what?
Yeah, exactly.
It's, where are all this transform? It must be somewhere. All the models of the transform. Like this, we put a sentence, but I'm looking for telecom. Is there any specific to that?
Hugging Face.
Hugging Face has
I'll talk about it.
more.
All right, guys, are we ready again?
We just said so. 16 hours. 16 hours.
Yeah. Hello, guys. All right, folks, welcome back. I hope we had some intuitive understanding of what we are doing. Now, let's look at the original paper. When we read this paper, it should feel very simple. I must also say, it is a research paper, right? So long as you get the main ideas, it's fine. We won't go over every single detail. So, guys, please pay attention now. Come back. Are you? So Bert and Roberta, these are, what are they? They are transformer models. Have such a new state-of-the-art performance on sentence pair regression tasks like semantic textual similarity. Right? See, guys, if you can do textual similarity, you can do very well. So today, you can feed a transformer to text and ask, are they similar? So theoretically, you could have, you don't need to create vectors. You can just store a list of just a database of text. Anytime you get a query, you go compare it to all the text. Are we together? Using a transformer. But why is this not a good idea? It goes on to say, however, it requires that both sentences are fed into the network, which causes a massive computational overhead. Right? Finding the most similar pair in a collection of 10,000 sentences requires about 50 million inference computations, 65 hours with BERT. Right? So 10,000 sentences is nothing, isn't it? Any respectable corpus of documents would have like hundreds of thousands of documents. When you chunkify it, you will have millions of chunks. Right? So this is written in 2018. So it's very interesting. People were trying all of that. So in this, I will skip some part of it. So one of the main ideas is that, why do we create vectors? Because vector searches are fast, isn't it? Why do we even bother going to a vector space? Because when we go to the vector space, finding neighbors is very fast. We lose something, of course, because it's an indirect path, right? You're not comparing a query against text. You're comparing a query's vector against the vectors of other text. It's an indirect bound. Right? So you lose something, a little bit, but actually you don't lose much. And this paper, I invite you to read this paper. Unfortunately, our course portal is in a bad shape. I may have to reconstruct it from scratch, but I'll do it as soon as I can and start posting things. But let's use Slack for the time being. Right? So the main idea is this. You feed it 2 sentences, which I just explained to you, and the triplet clause. Does this look like the thing that has? So these people have written the equation in terms of similarity rather than distance, opposite concept, but it's the same thing. So if you minimize distance, you maximize similarity, isn't it? That's all it is. And you are doing that. And what it shows is that when you do it, it turns out to be pretty good. The performances are very good. The results are very good. I won't go into the results. It suffices to say that the verdict of history is the years that followed is that this has become a workhorse of the industry. In fact, this is how you do RAG. This is how you do semantic search. Right? The most successful use cases of AI at this moment, outside recommender systems, which are also dominant. But if you look at the transformer architecture in recent years, the most dominant use is of semantic search and RAG. Right? And in a way, this proves it out. This is a very simple paper. You notice that there is no mathematics in it. It is just text and talking about history and so on and so forth. I explained to you the sentence A, sentence B, that you look at how far apart they are or similar they are. That's all to it. That's all there is to this paper. I invite you to read it. Anybody has a question or something? It's a very simple paper, actually. Right? Now, what I would like to do is go on to some practical aspects. Right? So first advice I would give you, and obviously learn with me, learn in Udemy, learn in Coursera, learn wherever you want. You will significantly benefit if you fill in some part of the theory, what is training, what is inference, and so on and so forth. Just enough of that. It will benefit you guys quite a bit, because what I observed is, and this happens with every batch, every time we have a batch, the first session, there are a lot of questions like this that come. And eventually people figure out that, and from experience, that it's very easy to fill in the background. Right? You can fill in the background. And when you fill in the background, you can run much faster. Right? So do that. That is one. Now, what I will do is explain to you how to set up your machine to do the development, to run through these Jupyter notebooks and so on and so forth.
Can I ask a quick question?
Yeah, sure, of course.
Yeah, I just noticed the word glove embedding. So I worked on the glove embeddings like a few weeks ago. So the model that, the Jupyter notebook that you were working, can we do the same things and we don't use the transformer model, but we use the glove embedding? Will it do the task?
Very good question, Shraddha. See, glove embedding and word embedding, the word2vec, these are word embedding technologies.
Yeah.
Before transformer came, before sentence word came out, they were the workhorses of the industry. The best that we could do in 2017, 2018, early 2018 was literally a word2vec or glove.
Yeah.
And prior to that were TF-IDF and other things, right? And compared to TF-IDF, word2vec and glove were substantive progress.
Mm-hmm.
But the problem with word embeddings is this. Suppose I give you a sentence.
Mm-hmm.
I give you, let's talk about Apple. What am I talking about?
Mm-hmm.
Right? Not enough context. The word Apple is not descriptive enough. It's a homonym. It has multiple meanings.
Mm-hmm.
I use the word banking.
Mm-hmm.
A bank has multiple meanings. Maybe your plane is about to land and it's banking to the left.
Mm-hmm.
You go to the bank, or you just swam across to the river bank.
Mm-hmm.
So words in languages have multiple meanings. And the problem that happens with all of these algorithms is it misses one point. The meaning a word has is most of the meaning that a word has, or what it does, is in the sentence rather than in the word itself.
Mm-hmm.
So I could have said the XYZ is ripening, and soon we may be able to pluck it from the tree and eat it. You probably would be able to give a lot of meaning to the word XYZ, right? Even though XYZ doesn't exist in the dictionary. So meaning comes from context. The lesson that Transformers brought, our attention brought, is meaning comes from context. And what semantic search, sentence embedding does, that's why we use the word semantic, is because the realization that you need more than a word to get the semantic extraction. Are we together?
Okay.
So, any other questions, guys? With that, I will now take you through the process of setting up Anaconda. There's a Python on your machine. We will standardize on Python because it's a dead simple language. Are we together? And I will do the setup also along with you. I'll try to repeat it after you. Right? So whatever I have on this machine, I'm going to write it out so that we both have a clean slate and we'll work from there. Let me do that. If you're looking at my screen, what I'll do is I will go and delete whatever I have. Oh, desktop. Okay. This is a Windows machine. I'm not that familiar with Windows. I'm mostly a Linux person. Yeah. So you'll find that I have a directory called Anaconda. It should be somewhere here, Anaconda 3. I'm going to deliberately delete it from my machine so that we both start from the same setup. And so let's go, while this is being deleted, let's go and I'll give you two things, two references, guys. There is this website called sbird, sbird.net. Please bookmark it, sbird.net. This is the home for Sentence Transformer. And as you can see, this is a pretty respectable project. It has 13,000 GitHub stars. You can add one more of your own. Installation, you can't install till you have installed Python on your machine, so we'll do that first. But it's pretty simple. So the activity for this week is, guys, I'm not going to give, I was going to give out a small project, but I won't. Instead, I'll give out a homework. Become familiar with this library. Are we together? Make yourself here familiar with this library, and I'll give you a simpler, very simpler homework associated with it. The homework is this. Just take some documents that you have, right? Some things that you have across 2-3 subjects if you want. Break it up, create use pretty much the same code, create an index out of it, vector index, okay? And then search in it and see how the search results look. Are we making sense? It's simple exercise. It's a very small extension of what we have done in the Jupyter notebook. So you'll have to study it, and then you have to take it a little bit forward. Right? So let's go to Anaconda. Do you see at the top right, there is free download? Are we all seeing it, guys? Click on that and download it. It should download on your operating system in the usual place. Where is it downloading? So it should download somewhere, and you should be able to go to your downloads, and it is still downloading somewhere. Or not. I hope it is. Oh, yes, it is downloading somewhere. Yes, here we go. Wherever it downloads, go and double click on it, install it, use your operating system's way. And just go through the installation process. It will be a very click through install to install Python. So it's saying the directory in my case is not empty, means it hasn't been deleted fully yet. Okay, I think Anaconda is gone. So I'll try again. Okay, I'll just put it on Anaconda 33, a new directory, and see. Anybody? And once you have installed it, you have essentially your Jupyter environment fully set up. That's all it takes. I mean, sorry, the Python environment fully set up. That's all you need to do. Now, one thing, a couple of things I would like to mention about hardware, guys. Some of you are sitting on old laptops. Some of you are sitting on different things. So there are two ways of going about it. One is you can just continue to use what you have and see whether it works or not. Right? Transformer models are a bit compute heavy. If you don't have a good GPU, in fact, if you don't have an NVIDIA GPU, things may run rather slow. Right? So the best advice I would give you is you can use a cloud VM, which has reserve yourself a cloud VM, and with a GPU, NVIDIA 4090, I mean something, right? Take it. You don't need too much memory. Just 16 gigs of RAM is more than enough. Having a GPU there is good. You don't need too much space. 100 gigs of data, 100 gigs is more than enough for the early stages. Right? And at this moment, like practice on that. And when the time comes, you can of course access the big servers. The other thing is each of these rooms has a workstation. If you don't want something local, if you want to come here and work, you're most welcome to come here and work on the machines. They are at your disposal. And then I would suggest that amongst the cloud providers, the least expensive, Amazons and GCPs are very expensive. The moment you ask them for a GPU, GPU card, those machines get very expensive. RunPod is a small company that's getting pretty popular. RUNPOD. Run. You can try that. POD. RunPod. It's a provider of, and a lot of people who are learning AI tend to use RunPod. Now, one basic practice about VMs in the cloud, guys, if you're not familiar with it, use it and immediately shut it down. Don't delete it. Shut it down. When you shut it down, you're still paying for storage, a few pennies a day, but you're not paying for running that machine. But if you keep it running, the meter is going on by the hour. It's like having a taxi waiting outside your house while you are happily having your nap. Right? So don't leave your VMs running, especially the GPU VMs are quite expensive. Are we together? Do that. The last piece of advice that I'll give you is become familiar with Google Colab. It's a free service. Colab.research.google.com. If you go to, you will get for your account these Jupyter notebooks, which are absolutely free. Now, if you pay $10 a month, you get access to better hardware. And I'm told that if you pay $50 a month, you get access to really good hardware. Right? So a lot of people I know, for example, in the previous boot camps, what they would do is they would do some of their labs in Colab and some they would do on the hardware here. They didn't go out and buy an expensive machine for their own. A lot of other people, on the other hand, bought machines because they wanted the convenience of a machine under there. See, your productivity goes through the roof if you have a machine of your own, right? Now, machines come in different sizes. You can go buy it from a vendor, like a Dell or something like that. Make sure it has a good RTX NVIDIA GPU. Don't get it with AMD GPU. They don't work. For AI, they don't work. So you have to get an NVIDIA RTX series GPU. 4090 is the benchmark. NVIDIA RTX 4090. If you can't get that, so if you put that, you're gold, pretty much. And a lot of people, half the class ended up getting a machine. Now, what they did is most of them, amongst us, there's a person, Sukhpal, you heard him talk. He's our IT, and he's actually a very talented person. He's a surgeon. So if you need a surgery in a hurry, he has a scalpel and things ready. He also is a video filmmaker. In fact, some of the famous scenes in movies in India, he has been the videographer of. And he also loves making good machines. He won't make silly machines, but if you want a high-end machine, like with a GPU, he loves making that. And he does it at cost. In other words, he doesn't make much of a profit at all. So it comes out far less expensive than going to Dell or buying it. So in other words, you have many choices. You can make do with the machines, Colab and the machines here. You could build yourself a machine. You can buy yourself a machine. You can use Colab, or you know run pods, etc. Are a good choice. Okay. Now I have posted all of these notes on the website, but let's see how long it takes for me to recover it. It seems pretty bad. Are we together, guys? Now, once your Anaconda is installed, what it should do is it will bring up an application when you see this green thing, it means the Anaconda is launching. Python is a little bit of a slow language. So most of the machine learning libraries in Python actually they use Python just as a front end. They are backed behind with C, C++ code, very fast C, C++ code. So you should see an interface like this. Are we all seeing this? Right? Once you come to an interface like that, in the beginning at least, what we'll focus on is Jupyter Notebook. It is the first row, second item from the right. And this is what you will launch. When you launch this, and this is only for those people who are new to Python, then you can visit directories, you can see things. So for example, in my case, I have some projects here. I can go into some of those. For example, today, what we were talking about is here. Is this the one? Yeah. I was showing you guys this project, isn't it? Yeah. Actually, the file is the other one. Sorry. And so I'll create a totally new file and show you. What you can do is you can say, let's say you are here. Don't show anymore. Okay. So Jupyter itself seems to be going through some revisions. Do you see this new button here, guys? You can go to New Python. And Jupyter is a very popular environment to get started with Python. So suppose you say print. Hello world. You should be able to run it. You see the output came here. Are we together? So I would suggest if you're really starting from the basics and you are trying to get yourself familiar with basic data science constructs, make yourself very familiar with Jupyter notebooks. Okay? How many of you are not familiar with it? A couple of guys. Okay, so then this week, that's your main focus. You should do that. And if you get stuck, come and talk to me. or reach out to one of the teaching assistants. They'll help you, and that's how you do the coding. Now, for you to make progress with this, remember guys, the only requirement is that if you work on a machine without a good GPU, things will run slowly. But it's all right, because at this moment, the first few weeks, you're not going to do anything very heavy lifting. Right? Now, the other thing that you need to do is form your teams. Right? At this moment, you guys hardly know each other, but as you gradually do, you can form. See, guys, it's not too critical. You form a team, you don't like it, you move to another team, or you go single. Right? There are lots of lone wolves you can do. These projects can frankly be done alone. The only reason you would like to pair program or form a team of at least 2 is in case you fall sick, somebody is making progress, right? Or helping you catch up. So from that perspective, it helps to pair program. I will hear that. Now I'm going to show you a tool of where.
Yeah, so instead of using GPT, why can't we use Google Colab or something? Or,
Yes, I just introduced you guys to Google.
Oh,
Colab.
okay. Oh, perfect. Sorry, I had to take a call in between. Yeah, sorry.
In Google Colab, directly you can run the program?
Yes, you can run the programs.
Oh.
All of these things you can run there.
But we don't have to configure or.
No, if it says some library is missing, so I'll give you an example. Suppose I say some library is missing. Let's say sentence transformers. How do I install sentence transformers? Yeah. Sentence transformers.
Pip 3, right? Pip 3 install.
You don't have to say pip 3. Pip install is enough. And when you run this,
They're using Jupyter learning.
oh dear.
Like Anaconda knows that.
Yeah, nowadays, like if you do pip, right, it's assumed that.
Sometimes like the laptop may have Python 2.7. So
oh, okay. If you have
that,
old
that conflicts will be there.
Right. So guys, this is it. Now I want to introduce you to some resources that are extremely useful. So this is a Google Colab. It's free. But if you want a little bit more resource, give them $10 or $50 a month. They have a tiered service. You can pay them more to get GPUs, better GPUs and so forth. But it's pretty good actually. They use their spare capacity to let you have fun. Right? Now, there is a very dominant place. Many people say these pre-trained models, where do they live? In the public domain, they all live here. Most of them live here. Right? Huggingface.co.
Hugging Face has something called Spaces, where it's all hosted on their site. There's audio models, LLMs, all these transformers are on there. And you go to huggingface.com to Spaces, you can try any of them out straight from the web browser.
Yes, thanks for mentioning that. Yes, you could use the Hugging Face Spaces. And you'll find that a lot of such services are there that you can use. But become familiar with this. One of the questions is how many models are hosted here? Let's go find out. Because every time the number keeps changing. What is it? 500,000. Right? And with time, every day it grows. Right? Now, there are models to do everything. Do you see all of these things here?
So how do we choose the most used or most efficient models?
Yes. So the way you do that is what you do is you talk to people, and the other thing you do, generally, it's a good idea to pick a model that you know about. Like what people have done is to get a name for themselves. Every time they get a model and they fine tune it even a little bit, they push it to GitHub, even if hardly anyone will ever use it. Right? So it's just a way for people to get known. So A lot of these come up, but one way to look at it is they have trending. Do you notice that if I take any one topic, let's say image to text, what can I do? I can look by, sorted by most liked, most downloaded, recently created. If you look at most downloaded, yeah, this is the VIT GPT-2. This is a much older model, but still doing well. Trending. Which is trending? Well, it turns out that Salesforce Blip 2 is still doing pretty strong. So guys, all of these words are strange to you, but as you work in this bootcamp, these VITs and these blips and lavas, you'll encounter all of them. But today we started with the simplest one, a sentence word. Are we together, guys? So come here. It has pretty extensive documentation. Make yourself familiar with it. By the way, it will be overwhelming. When you come to it, the first thing is war. AI is a vast field. And the amount of activities that have been done, the amount of libraries that come out, very, very good quality libraries to get work done. There are many libraries that will get work done. Every day, lots of research papers are published. And as you know, Support Vectors runs a weekly series. How many of you come to that weekly series or know about it? Okay. If you don't, every Wednesday at 6 p.m., we do one research paper reading. It's free to the public. Right? You're welcome to come to it.
Do you do that online where we can participate remotely?
Oh yes, it is. It is exactly in this mode. Yes. It happens every Wednesday.
Yeah, can we share the link?
Oh yes, if you just go to meetup.com, support vectors, even I don't have it.
youtube.com/support vectors.
That is it. Yeah, that's right. You see the live streaming there. And if you go here, meetup.com/support vectors, we have a meetup group. And in this meetup group, let's see, upcoming events. There's the Tuesday session, there's a Wednesday session. So the Wednesdays are regular, every Wednesday. And also, you should be aware that most of our talks now, like because this is a very long talk, I'll make it private, this YouTube video. Oh, sorry. Let me go to support vectors. So the talk that we just had, oh, here is a talk we are having. It's live. So all of our talks are here. You can go find it, and after some time, I'll hide it or make it unlisted, but you'll still have a link to it. Needless to say, when you have the course portal, it's much more organized, like it's there all in one place. So I invite you to come to the Wednesday talk, evening talks. And that way, you will read 52 papers in 1 year. It all adds up. Were there 52 papers worth reading in 2023? You bet. The pace of research is, and breakthroughs, the pace at which breakthroughs are coming is just unprecedented in history. And I'm told what's happening in AI is happening in every subject. Like more knowledge is being created in every 2 years than has been created in the entire history of mankind. The pace of development in every field has gone up so much. So if you have been relaxing for a couple of years in your workplace, you're really behind. You know only half the things the world knows.
You have a sense of humor.
All right, guys, any questions? So what are the tasks? I'll post to Slack these Jupyter notebooks. I'll do it in the evening. I want to clean it up a little bit, and I'll post this. I'll make sure that they run. Everything is fine. Then I'm going to post it. When I post it, I'll also post a README that how to run it. Now, one thing I must say about the notebooks, run it in sequence. You see that 00A, 00B, 00C, and then semantic, the corpus, and then finally the search. Do that. And Hugging Face, let me just use it as an introduction to Hugging Face website. Suppose I want to do, see, most of the tasks that used to be rocket science a few years ago, today has been trivialized down to somebody has already created a library, just use the library. Right? So your first reaction to any problem should be, download, not a library, download a model. First reaction should be, is there a model already? If there is a model already there, use it. Then the question comes, is it good enough? What will happen is that for casual use, it will be good enough. But the moment you try to do anything serious with it, you will want to fine tune it or further train the model sometimes. Are we together? Or do some adaptation of it. So then you go and do. But this is a simple example. Sentiment analysis. Suppose you see text. What is the sentiment behind it? Yeah, notice that what I have done is transformers, by the way, is Hugging Face. You install transformers and then you create a pipeline for sentiment analysis. And you'll realize that that pipeline works like a charm. Yeah. You give it a text and it will come out with a label negative. For example, this used to be actually a difficult thing for language models before this. A few years ago, if you gave a sarcastic comment like that, the NLP sessions have proved useful so far, and then you end it with none. Right? The models used to get confused, but now you notice that it's practically sure, 99.8% sure that it's a negative sentiment. You see that, guys? So play with it. Hugging Face is a boon. There are lots and lots of models that you can just download and do your casual work. And in the LLM 1 bootcamp, guys, I would suggest that half the time we will be doing very useful things using existing models. Are we together? We need to first learn to crawl before we run or before we walk or run. Right? Then we'll learn fine-tuning and we'll learn complicated architectures. Right? And does it always get it right? Not always. Sentiment analysis is notoriously difficult. For example, look at this. It says it's a positive sentiment, not so thing. But anyway, I brought this up just to illustrate that Hugging Face is there and you can download lots of models. Now, one of the things that people ask is, okay, if the models are there, what do I do? What you do is, for example, domain-specific models. When you say bear, a bear market, a bear, in the common language, it means something else. To the fintech people, financial people, bears and bulls have strong meaning. Right? So if you say the trading is very bullish today, or today the market rallied, Nasdaq gained, but not much, or something like that, you can actually get meaning if you use a finance-aware model. How do you create a finance-aware model? You take a foundational pre-trained model, and then you further train it or fine-tune it on finance data. Now, fine-tuning, it turns out, doesn't take that much data. 10,000 rows of data may be enough to fine tune. Even 1,000 rows may be enough to fine tune. Are we together? Right. So, for example, in a prior workshop, one of the homeworks I'd given is you had to tune a model, fine tune a model to tell the difference between two California trees, popular trees here, a pepper tree and the weeping willow. They sort of look alike a little bit. They both have drooping leaves and branches. And you had to exceed the accuracy of a pre-trained model. People had to go take pictures of pepper trees and, oh, Saurabh, you remember that?
Yes.
Right? Yes. You remember that project, yes. And so people did that. And most of them, the engineers, you can rest assured, they only love coding. For everything else, they're lazy. Right? So most teams brought maybe 100 picture of 100 each. Right? And that also, God knows if they actually took photographs or they just scraped the web for it. At the end of it, you had a much better model. Right? So whenever you train a model for a custom purpose, you start with something, in the vicinity of what works. Right? And from there, you don't start from scratch. You start from a nearby point and then you fine tune. Right? So that's what we do in this field. I thought I'll give that as an example. So one thing, if you do want to, I don't know, if you want to do some self-study on your own, right? There are lots of very good books available, completely free on the internet. Of course, there are YouTube videos and whatnot. For some of you, if you go to YouTube, in the video series, you'll find many series of videos on this topic because it's a hot topic. But there is one channel, 3 blue, 1 brown. I hope I get that right. Yes, these people make very good sort of explainer videos on many topics, mostly to do with mathematical topics. It turns out they made a small series of videos on, for example, backpropagation. So let me do 3 blue, 1 brown, back. How do neural networks learn? Like, how do you train the model? Backpropagation. Yes. So if you look at this video, it belongs to a series. Yeah, it belongs to this series, which has just 4 videos, but they're pretty good videos. They'll give you a very basic idea of how neural networks get trained or how machine learning works. Are we together? Right. I would suggest watch these videos. These are short 10-minute videos, 10, 15, 20-minute videos. It will give you a basic sense of what is it to train a neural network or an AI model. All right, guys, that's it. That's all I have. Now, there's some books here that you could go to. One of them is Deep Dive. So Dive into Deep Learning. This book is freely available. You can buy a copy. It's a very good book. A lot of people find it useful to just study this book. Right? Keep it as an aid if you want to understand what these things are. Like I got a question about the transformer architecture. Assuming that you're not coming to the Tuesday class, then you want to know what is so special about transformers. I think, Shraddha, it was you who asked this question. So then you can just get a quick sense by going through these pages. Are we together? So this is Dive into Deep Learning. If you prefer a little bit more mathematical treatment, then there is Understanding Deep Learning. This. Once again, this book has just come out. It's an excellent book. and the PDF is here freely available. Right? It's a voluminous book. It's a beautifully written book. I mean, if you look at this book, the author has done an amazing job making it freely available and writing a very good book. If you look around, you'll see lots of colored pictures, lots of very clear explanations. It is there in this particular book called Understanding Deep Learning. I'll post all of these links to Slack. Are we together? So you can pick it up from Slack. And that's all I have, guys, for today. Anybody has questions? So guys,
I have one comment. It looks like there's about 25 of us that are remotely connected on Teams, unless the class members joined in as well.
Okay.
I want to throw a
I'll give you the number, Sarah. 1 second. How many of you are logged into Slack Zoom at this moment? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 10 people in Zoom are from here. So 15, let's say remote. Please go ahead.
Yeah. So I want to throw out, who's looking to join a team, who needs availability. Should we do that conversation on the Bootcamp channel?
Yes, on Slack. On Slack.
Okay.
That would be good.
Because I was wondering if it would make sense to create another channel, but for team matchup, so we don't clutter the main, but we can put it on the main as well.
Okay, as you guys want. I mean, we can easily add extra channels.
So, Asif, what are the timings of the bootcamp? It's generally every Sunday, 10 to 10?
That is right. So I'll be here till 10 to help any one of you who wants to talk to me. But you guys are free to leave pretty much. Now, if you want to do this assignments from home, do it, or you can stay here and do it. Right? So for example, if you want to set up your environment, run through, read SentenceBird, the website, the documentation, play with it. And as you play with it, you get stuck and you need help, I'll be here.
So generally it will be 10 to 3 with you, and then it is self-study. Is that?
It is usually 10 to 5 with me, right? And after that, it's self-study. And throughout the week, as you need help, you keep reaching out.
Okay.
And now I'd like to move to the last item that we have. We call it the Cambrian explosion, right? If you see the presentation, it is. So as you know, the word Cambrian explosion comes from geology. At one time, Earth, suddenly life forms, different species of life forms just exploded on Earth. It was an amazing time. Lots and lots of new species started showing up. It's referred to as the Cambrian explosion. We see something similar happening in artificial intelligence. You see that almost overnight, there's an explosion of big ideas, big developments, big breakthroughs, big neural architectures, literally happening at an unprecedented pace. Right? It has the feeling of a Cambrian explosion. Now, one thing that we do to enrich our community, but today I'll just mention it because you guys are not prepared. Throughout the week, guys, learn about AI. Lots are happening. Whatever piques your fancy or your interest, pick something. Read a little bit about it. Enough to mention it. You don't have to talk about it. Enough to mention it to your other participants in this cohort, right? And then next Sunday when we meet, we'll have our Cambrian explosion conversation at the end of the day. It is the last thing we do. It's a social thing. We drop, we mention what we learned. Does that sound interesting to you? It could be a bit of news. It could be like, oh, Europe is putting together their European AI Act, right? Or something like that, something of interest that will benefit everyone to listen. At the same time, of course, please keep sharing your insights onto the Slack channel, whatever you discover. And you'll notice that the Slack channel will get quite busy. Lots of postings will come, lots of things will happen. So just to trigger off the Cambrian explosion, as you guys know, from my side, the two contributions would be, of course, which I'm sure everyone would have noticed. Just do you know about Sora?
Yeah.
All of you know about Sora. Sora is an amazingly realistic video generation framework OpenAI has come out with, and true to the name OpenAI, we know nothing about it. Then Meta has come out with another framework, very good, very effective, which is video understanding, and it is called JVaper. I'll be covering JVaper in the first week of March in the paper readings, right? And we'll use some of that in this particular bootcamp, but towards the very end.
So what is the best way to learn all the latest things happening on the models? Where do we get updates, like any Twitter? Where do we get all these updates?
See, I don't do social media at all. The only thing I do, even a little bit, is LinkedIn, because now I'm the CEO of Support Vector, so I have to be a little bit visible. But I am not a very social person. I don't have a Facebook or a Twitter, much of activity there. So I'm the wrong person to ask. What I do is I go to Archive Sanity and I look at the best. I just glance at all the papers published every single day. I read the abstract.
Oh, where is that? I mean, what is the, how do we go for the archive?
Archive Sanity. It is this. Archive Sanity. And there are many similar websites. If you go here,
okay,
you see that the papers are mentioned here.
Okay.
So just glance through it, things that interest you, dip into it, read the abstract, and you see that these abstracts are here. Right? So I study the abstract. This is my newspaper. This is the best way to keep in touch.
Thanks.
Yeah. So I'll give you an idea. Like, for example, we are looking at it today. Right? What does it say? Hierarchical state space models for continuous sequence to sequence modeling. Now, this whole title would look very arcane. So let me unpack it for you. These days, there's an alternative to the transformer. It's called Mamba. It is a state space model. Now, so what state space models are, again, we'll leave it to Tuesdays, right? But they're an alternative to attention-based models. Somebody has created hierarchical state space models. So that seems to be the innovation. For what purpose? For continuous sequence to sequence modeling. So when do you have continuous sequence to sequence modeling? Most likely when you're talking about, I suppose, continuous data coming in, like as in sound, audio, or IoT data or something like that. I'm guessing, but you can read that. Reasoning from sequential data. No, sequential data is, of course, words are sequential data. We present. And also keep an eye, I mean, you shouldn't do that, but keep an eye on the authors. You can often tell the quality of a paper because you know how, if you have read the work of those authors in the past. So this one is, by the way, from Carnegie Mellon. Right? You can pretty much assume they will not let anything get published unless it's absolutely top tier. Right? So this pretty much, you can go with confidence, read the paper. Now, good thing is that once you get used to reading papers, most papers you can finish in a couple of hours, in an hour or so. So every day, read the abstract, pick a couple of papers. You can't read more than 3 papers a day. I mean, otherwise you won't be able to do your job and the rest of the thing. If you want to study paper, pick a few good ones.
Can you show that website?
ARXIV Sanity. Right. Let me post it to Slack. Here we go. This is it. And while I'm at it, let me post the other links also. I was talking about the meetup. This is the meetup. And I was talking about the YouTube. This is the YouTube. And what else was I talking about? Hugging Face. This is the Hugging Face.
Also the deep learning stuff, the two websites, MIT one. Yeah.
Yeah, that is right. Deep learning for this one.
Recording for today's session.
And the recording is all there on YouTube.
No, you cannot access the website. Oh, YouTube.
And
we talked about 3 blue, 1 brown.
yes, 3 blue, 1 brown. Let's look up that. Yeah, this link also. And finally, there was another book that I talked about. So guys, do you feel like having a little bit of a fun? There is a website. If you're new to neural networks, then I usually, whenever I teach neural networks in whichever form, I get people to see how it works. Right? Let me show you how it is working. So you see these 4 data sets. You want to ask a neural network to draw a line to separate or draw some separation between the yellow regions and the the regions of the blue dots. Right? Suppose you look at this data. Can you visually tell what would be a good line? Just a diagonal would do, isn't it? And so let's try to run it and see how quickly it discovers the diagonal. Almost instantly, isn't it? But then this neuron has 3 neurons in it. What happens if I decrease the number of neurons and run it? It still manages to do a good job. I decrease it, make it even simpler. The simplest neural network is a network of 1 neuron. So there you go, it still works. But if you complicate the problem, then it won't do. You notice that it's struggling, right? Let's increase the number of neurons and see what happens. Got it, isn't it? You could increase a little bit more and see what happens. Actually, it's taking a little bit longer to converge, but it will eventually. It will suddenly collapse to it. Yeah, you see it's beginning to collapse now. And there it is. And you could add more layers and that will accelerate it. You notice that if you add more layers, it learns quickly. It's a mystery, actually. We are still trying to understand why going very deep. I mean, we do understand some of the math and some we sort of understand, not quite. Why making very deep? Come again?
What is this website?
Yes. So it is called the Playground, TensorFlow Playground. It was all there on the portal before I lost it, so I have to put it again. Where is that? Go and play with this resource and let me see what else. Oh, deep learning, understanding deep learning. Yeah. This book. You can buy this book or you can just read the PDF. One thing that you may find useful is to go down and you see all the figures in the chapters. You can stare at the figures. I find that very useful to just remove the text, just look at the figures and to see what they are trying to tell you. And here's the slide deck. So for some reason, it's causing me to log in. I don't know why. But anyway, that's that, guys. So, oh, here we go. There's a PowerPoint. That's opening up on the other screen. How do I bring it to the screen? So you can see that it's sort of, what's the relationship? Obviously, it's hard to make much out of these unless you know. So the author helpfully points out to a review in Amazon for the book. As it says, it's the worst book I've ever bought or read. I don't know why it got so good reviews. Don't recommend. It's extremely disappointed because what this person was looking for is a lot of code in the book. But this book, as the title says, is Understanding Deep Learning. It explains you the concept and doesn't have much code at all. On the other hand, the other book has code.
Can I ask a question on it?
Sure.
So, getting the results from existing database from a search, right?
Mm-hmm.
So, does that style of thing will we be working in this class?
Yeah. So what happens is when you get to semantic search, you begin to ask, if I can do text and I can do images and I can do video, why can't I do tabular data sitting in databases? And of course you can do that. Anywhere, anything. See, the state of the art of AI has moved so far that now these things are capable. A lot of the things that you thought only software engineers can do, LLMs can do, AI can do. They're transformer models that write code. In fact, most of you are using the GitHub Copilot, isn't it, in your programming? But most programmers do use that. And if you really think about it, most of the code is written by AI these days. You just give it hints. You're just prompting. When you're coding, you're just writing a comment, and based on the comment, it goes and writes the whole code for you. Right? So we are now moving into a world in which many professions are history. People have just not realized it. Software engineering is certainly gone. Right? It will shrink. Like you remember, I have an analogy during the .com days when HTML had just come out. If you were an HTML developer, HTML writer, and gosh, if you could even do a bit of JavaScript, you would be paid an insane amount of money. At a time when deep C programmers used to be paid 60, 70,000, these guys were paid 200,000. Right? But what happened after some time? Tooling came, and today you don't pay those C HTML developers that sort of money because the tooling takes care of it, isn't it? There is still programming. There's still some amount of Angular and React and so on and so forth writing. But even there, with AI coming in now, most of the coding is AI assisted. So as coding is AI, and almost every profession is AI assisted. In fact, one senator, was it a senator or a congressman, was caught because he managed to pass a bill into law, and it turned out that AI had written that bill. Right. So this is how the world is going at this moment, right? See, one example I give to people is if you see a steamroller coming your way on the road, what's the safest place to be? A road roller. What's the safest place to be? On the steamroller, right? In the driving seat. AI is this big steamroller or the road roller coming at you. Whatever other software engineering you're doing, now is a good time to abandon it and quickly. Sorry, I take that back. Don't abandon it. Bring AI into it. Whatever you do, you have deep expertise in it. Bring AI into it. Be the thought leader who is bringing AI into your company. But get into AI if you're not. I mean, I'm preaching to the choir. The very fact that you guys are sitting here and on remote Zoom means you see the importance of AI. Right? But for each one of you, there are 1,000 who don't. They're comfortable in their jobs. They think life will go on, but it doesn't go on. We are going through the biggest shift in history.
Convert the tabular database into a vectorized database.
No, you don't do that. You create, it's slightly different. What you do is you convert it to text oddly and you vectorize the text. Right.
pick up the values in the cells, form a sentence of it.
Yeah, you do something like that. I mean, there are different techniques, but that itself is a subfield that people are actively exploring. But generally, if you have text, especially in your database, then of course it's a no-brainer.
Yeah, let's say it's all text.
Oh, then of course it's a no-brainer. All right, guys, any questions? Any thoughts? Was it fun today? Like, did you feel you learned an important technology?
Yes. Yes.
Oh, yeah.
Good, guys. So I'll let you be. Please continue to do the labs. You can do it now. You can do it later. I'll be available here. You can ask me questions. I won't be on Zoom. I'll close the Zoom, but I'll be in the office. And if those of you who are remote, reach out to me on Slack and I'll get back onto the Zoom immediately. All right, guys.
Skate around.
Yeah, I'll post the labs. I'll just clean it out a little bit and post it.
Skate around.
Kate has got home.
She didn't add me to the 2024 cohort.
Let me add you. So anybody who's not added to the Zoom, please reach out to me and I'll add you.
Into Slack.
Okay. Slack is in there. This is Slack.
So Asif, if you want to see the recording, I just Google on the YouTube.
No, I'll take you there. See, you go to YouTube. Are you seeing my screen?
Yeah, I am. Yeah.
If you go to support vectors, go to live.
Okay.
And do you notice that there is actually a live session? As I'm speaking, this is being broadcast.
Okay.
These videos will remain here. Yeah.
All right. Thank you.
Nice, Sanjeev. Sanjeev, was it fun?
Yep, it was fun. It's a lot of learning. I'm just trying to get used to.
I don't know why it's not reflecting in support of PCI.
It's not reflecting. I can reconfirm that you're right. 2024. 2024 LLM. And there you are, Prashant.
So Asif, about Tuesday, can we attend a Tuesday class with this bootcamp?
Oh yes, guys, those of you who want to attend the Tuesday class, all you have to do is, I'll post the Zoom link. I believe it's the same Zoom link, but I'll confirm and post it and just come to it.
And what time is it?
7 p.m.
It's 1 hour. It's only 1 hour on Tuesday.
I'm sorry, please say that again.
It's only an hour class on Tuesday?
Yes, yes. It is from 7 to 9:30.
Okay, okay.
So, which you posted certain links, right, in the cohort. So, so it is showing us a joint AI 2024 along with this one. But
AI 2024 is not the one. 2024 LLM Bootcamp. Where are your channels? Oh, you may have to add. Oh. Browse channels. Okay.
Yeah.
2024.
Everybody do something.
Where is this one?
we have to search it.
Idea won't come one day. But I keep talking to customers, they keep seeing guidance.
Something weird.
The 2024 LLM bootcamp.
Yes, 2024 LLM Bootcamp.
This is the old one.
Yeah.
In telecom.
Let me try. Add a channel, right? Add a channel.
Sentence
Here is that 2024, right?
Are you able to get onto Slack?
Yes. No problem. So one question, quick one. Are you
you added, is the same Prashant Gupta, or can you check the email?
For those of you who are remote, do you need any help?
These
are your results. So all you need is
Shraddha?
going from your.
No, I think just we need
Go
homework.
ahead.
Yeah, just we need homework, Jupyter file we can work on, and
Yes.
yeah. And if you introduce us to the TA, that would be good too.
Sure. And I'll introduce you to all the teams.
Yeah, yeah. And then we can, I don't know, how do we partner for project? Actually, I will be on site next week, so it would be easy. But now
You should do it solo because you have that level of commitment. You can just start by just going solo, lone wolf on it. And then as you meet people, if you like somebody, then great. Or you like some team, invite yourself into the team.
Okay.
Nice. All right, guys, I'm about to close the Zoom. Anyone here? Bhavan, anyone who would like any help? Vanu, bye.